Charles Augustin de Coulomb was born in France in 1736. After finishing school, he became involved in structural, fortifications, soil mechanics, and other fields of engineering. After a while of constructing fortifications outside of France, Coulomb returned to France and began experimenting with electrostatic forces. Eventually, he discovered the relationship of the force between electric charges, which later became known as Coulomb's law.
Charles Augustin de Coulomb made calculating electrostatic forces simple with his formula. The scalar form of Coulomb's law is an expression for the magnitude and sign of the electrostatic force between two idealized point charges, small in size compared to their separation. The law states that the magnitude of the electrostatic force of interaction between two point charges is directly proportional to the scalar multiplication of the magnitudes of charges and inversely proportional to the square of the distances between them. No matter what happens, the total charge of the universe is at constant equilibrium.
All right, let's talk about electric force quantitatively. And this is called Coulomb's law, after a physicist who first developed it in 1783. All right, now we know that like charges repel and that opposite charges attract. It's almost like the universe is trying to hide the fact that there's charge. If there's ever a big charge anywhere, like a big positive charge, it's going to attract all the negative charges to it and try to hide itself, shield itself away. And at the same time, all the positive charges are going to be pushed away. All right, well, we know that this positive charge and this negative charge are going to attract each other, but how much? Well, Coulomb's law says that the force of attraction or repulsion is given by a constant called the Coulomb's law constant times charge 1 times charge 2 divided by the distance between them squared. So it's an inverse square law case, just like gravity. In fact, it's exactly the same as gravity, except that this constant, this Coulomb's law constant, is huge in this case. 8.98 times 10 to the 9 Newton meters squared per Coulomb squared. The reason for that is that the Coulomb is an immensely large unit of charge. You will never see an entire Coulomb of charge anywhere because it'll just strip electrons and other charge off of neighboring atoms until it has shielded itself.
This device is called a Coulomb apparatus. It measures static electric forces. The two spheres are charged electrically. And they will repel each other. The forces between these two balls causes the wire to twist. The water here in this container dampens out the oscillations. The stronger the force, the more the rope twists. There. A laser reflects on this tiny mirror and measures the twist. The laser's reflected light lands on this chart. The chart measures how much twisting is going on. Twice the force, twice the twist, twice the distance. All right, let's get started. The balls are initially uncharged, and so the chart over here is reading about 0. Initially, the balls are 10 centimeters away. Both of them get charged, and the rope begins to twist. Now, to what distance should I move the balls apart in order to measure half the original force. You see, the force is proportional to the square of the distance. This means that the original force was proportional to 1 over 10 squared, or 1/100th. The second force is proportional to 1 over radical 2 times 10 squared, which is 14 squared. That means 1 over 200, half as much. The correct distance is 14, because 14 is radical 2 times 10. At about 14 centimeters away, you get half of the force. This is because 14 is radical 2 times 10, and Coulomb's law, forces, decreases the square of the distance. Alright, whole new experiment. The balls are all charged up, and so over here we're getting a reading of about 14. Now I have this device which will take half of the charge off this ball. Now what will the reading be? Over here on the chart, we see the reading settling. This may take some time. At about 7. Half as much. From this experiment, we discovered that the force is proportionate to the quantity of charge. Now there's two charges, so we say it's proportional to the product of those two quantities. We also discovered earlier that it was inversely proportional to the square of the distance, and that's Coulomb's law. And that's Coulomb's law.